So the X component is disturbed, however, the currents will have opposite magnitudes on either side of the center line and thus will tend to cancel out the radiation, so therefore there will be no radiation. So what component is responsible for radiation? Is it the Y component, the Z, the X, or the A? So this is the most common slotted waveguide that resembles, I mean, it's like this. So figure 1, geometry. The most common slotted waveguide antenna. So front to end, so the front end or the open face of at the Y0 is the Z plane, where the antenna is fed here in the X and Z. The far end is usually shortened and closed in metal. The waveguide may be excited by a short dipole as seen on the cavity bag slot antenna or by another waveguide. So, wait. To begin to analyze the figure 1, let's view the circuit model. The waveguide itself act as a transmission line, and the slots in the waveguide can be viewed as parallel, shunt, admittances. The end of the waveguide is short-circuited. So a rough circuit model of figure 1 is like this. So figure 2 model slotted waveguide antenna. The last slot is a distance d from the end, which is short-circuited as seen in figure 2. The slot elements are spaced a distance from L from each other. So before we discuss choosing the sizes, they will be given in terms of the waveguide wavelength, which is the wavelength within the waveguide. The waveguide wavelength, lambda sub g, is a function of width of the waveguide A, and the free space wavelength for the dominant TE010, I mean TE01 mode, the guide wavelength is given by this. So another question, what is the shape of the hole in the waveguide? Is it a line? Is it a triangle? Is it a rectangle? Or a trapezoid? So figure 3. Oh wait, I forgot to discuss this. So the distance between the last slot and the end, the, is often chosen to be a quarter wavelength transmission line. Theory states that the impedance of a short circuit a quarter wavelength down a transmission line is an open circuit. So this will result in figure 2. Then it will be then reduced to this. So from this we go to this. So if the parameter L is chosen to be a half wavelength, then the input impedance of Z, ohms viewed a half wavelength away, is Z ohms L, is defined to be about a half wavelength. For this reason, if the waveguide slot antenna is designed in this manner, then all of the slots can be given as being in parallel. Hence, the input impedance for an N element slotted array can be quickly calculated as this. So the input impedance of the waveguide is a function of the slot impedance. So note that the design parameters are only valid at a single frequency. As the frequency departs from where the waveguide was designed to work, there will be degradation in the performance of the antenna. To give an idea of the frequency characteristics of a slotted waveguide sample, a waveguide, a sample measurement of S11 of frequency will be shown. The waveguide is designed to operate at a 10 gigahertz and it is fed by a coaxial feed at the bottom right here. That this is the coaxial feed, and this is the S parameter graph. See, we can see that the antenna has a very large drop in S11, around 10 gigahertz. So this indicates that most of the power is radiated away at this frequency. So the bandwidth of the antenna, if defined as where S11 is less than minus 6 decibels, it extends from about 9.7 gigahertz to 10 here, over here, giving a fractional bandwidth of about 8%. So there is also a resonance at about 6.7 and 9.2 gigahertz. Below 6.5 gigahertz, the wavelength is below the cutoff frequency and virtually no energy is radiated. So the S parameter graph shown gives a good idea of what the bandwidth frequency characteristics of a slotted waveguide will resemble. So the next one, this is I am going to show you a 3D radiation pattern for the slotted waveguide. This is it. This is the 3D radiation pattern for slotted waveguide. This was calculated using a numerical electromagnetics package called the FECO or FEKO. The antenna gain is approximately 17.5 decibels. So, so you can see here in the X and Z plane, or the also called as the H plane, the beam width is very narrow for about 2 to 5 degrees, and in the YZ plane, or also called as the E plane, the beam width is much larger, obtaining more pencil type beam using slotted waveguides. So the radiation pattern tends to have a very wide beam width in the E plane and relatively small beam width in the H plane. So the problem arises because the physical dimensions along the E plane is much shorter than that along the H plane. So we can say that the slotted waveguide is long, but it is no doubt thin. So in general, a longer antenna or longer array produces a much more narrower beam. So this problem can be circumvented by arranging slotted waveguides in parallel. So this is figure 1. So array of slotted waveguides fed by a single source. So by stacking waveguides as shown in figure 1, the E plane beam width can be greatly reduced in reduced in addition by adding a phase delay to each waveguide. The array of waveguides can be steered in the E plane. The phase delay can be added by varying lines length, then distinct frequencies will produce distinct phase delays, allowing scanning simply by changing the frequency. So this is an example of an antenna array. They are typically narrow. They are made up of hundreds and thousands of elements. So the this is the last page of my presentation. So power handling capabilities of slotted waveguides. So that's it. Note that the power decreases rapidly with the altitude. So this is necessary to keep in mind in designing radars for aircraft. So the max power is a function of the altitude and there will be further divided as CW or continuous wave and 1 microsecond pulse. So we go to the last question, I guess. So what is CW? Is it current wave, capricin continuous wave, and curriculum wave? So it's C. And that's all. Thank you.